Hello everyone. In continuation from the previous session on recursion and iteration, in this session we will see certain examples that makes use of iteration and recursion. So let us start in detail. The first concept that we are going to implement through iteration and recursion is binary search. As you must have seen this topic in your earlier classes, a binary search is a technique by which we can reduce the timing of searching an element. By searching an element, we means that we need to find the location of an element in a sequence data or in an array or in any other data structure where a collection of elements are stored, and we need to find out certain element using certain algorithm. Basically, for searching we have two techniques. One is linear search and another is binary search. In case of linear search, what we do is linearly or one by one, starting from the first index element of the array, we compare the given search element and move further until we find the match. So wherever the match is found before exhausting the given array, that index is returned if we follow the linear search algorithm. But the problem with the linear search algorithm was we need to compare each and every element depending on what element needs to be searched till the point we get the match. If the element is not present in the given array, or it is the last element in the given array, that would be the worst case, and there will be big of n time complexity, like the time taken to complete the search would depend on the value of n. It will be proportional to n. So to reduce that time, we make use of binary search algorithm. This binary search algorithm have certain condition. That condition is the data that we want to search should be pre-sorted. It should be in particular order, increasing or decreasing order. That is a precondition. Once it is with us, we can apply the binary search concept. How it works? We take the start index and the last index of given array. For example, here I am taking an array where some elements are stored in, and you know that in case of array the index starts from 0. So depending on how many elements we have stored, it will have certain last index. So those two values are stored in two variables, let's say first and last. In first, the index of the first element in the array stored is 0, and according to the number of elements, the last index is 9. So what we do, as it is already known to us, the data is sorted, we divide the given data into two lists or two parts, okay, based on a variable called mid. How we calculate mid? Mid is simply a average of first and last. You can say first plus last by 2, where this division is integer division. We ignore the floating value, we only take the integer value. So this would be the first step in finding the element. Suppose the element that we want to search is stored in a variable called key, and it is 63 in this data that we want to search, and also it is given this data is sorted. So as per the algorithm, we find out the value of first and last. So first is 0, last is 9, and then calculated the value of mid. 0 plus 9 by 2, that comes out to be 4 point something, but we take only the integer value, so it's 4. So once this mid value is found, what we do, we compare the element present at the mid position. If it is equal to the given key, then our search is stopped. See how fast it is. Maybe at the very first step we can get that element, but even if we don't find it, now we need not to search the whole array. As a second step, we need to search only the either first half or second half, depending upon the value which we want to search. At that point of time, when the element is not at the mid position, we'll check what is that element actually, 57, and the element that we want to compare is 63. So if the element that we want to compare is above this element, okay, in that case we'll search into the right half or last portion of the array, and if it is less, then we'll search in the first half of the array. And every time we redefine the content of array by shortening its length, we try to update first or last depending on whether the key is greater or lesser. In this case the key was 63 and mid element as the first phase is 57, it is greater, so we need to search the element in the second half. In that case our first value will update. Earlier it was 0, now this first will become the index of the element just after the mid position. That means it becomes mid plus 1. So now for this first and last value again mid is calculated, and that mid value comes out to be 7. At that 7 again if we check what is the value of key 63, whether it is less or greater. So if we see this example, 63 is less, so that condition gives the direction in which we want to move, either on the first half or the second half. If the value is 63, that means it is less than the element at the mid position, so we again update either first or last. In this case we will update the value of last. Okay, so now last would become mid minus 1, that means 6. So after this if we apply another step based on the new value of first and last, which is 5 and 6, and we calculate 5 plus 6 by 2, that would be 5, and at that point only that element that we were searching is available. So in only 3 steps or 4 steps we are able to find our element of interest in the data of size 10. That way we can say it is faster, binary search is faster. So this concept we can implement either using iteration or using recursion. We'll see both implementation, and before that you need to make sure the underlying concept. So basic idea is to identify the first value and last value, then find the value of mid, and from this mid value we keep on comparing the element that we want to search. We'll go in either direction, either in the first half or in the second half, depending on this comparison. Okay, so let us move to iterative implementation. In this case I am defining a generalized function here in which 3 parameters are being passed. One is the array address in which all the elements are stored. N is the total number of elements in the given array, and or you can say it can also represent the index, and key is the element that we want to search. So there could be some changes required if you want to actually implement in C or C++ language, but in general this is the architecture of the function. So as we are interested in finding the index of the first element and the last element as per the concept of binary search, we'll set first 0, last n minus 1. Iteratively what we have to do, we have to move from first to last, and we'll keep on updating this first and last according to the comparison, and we'll also find the value of mid. So how we are finding the value of mid? This floor function here is being used to represent that we need to take only integer value. So first plus last, whatever is being set, because 0, assuming the index starts from 0, first has been set to 0, and there are n elements in the array, so n minus 1 would be the last index because it starts from 0. Setting these two values, we can find the value of m in the while loop. This condition is required because sometime we may cross this or it would be equal. In that case there is no meaning of checking again, so this condition is mentioned here. If a of m is less than key, in this case what we are doing is we comparing the element at the mid position we just calculated, and if key is less than the element at the mid position, then what we need to do is key is greater, element at the mid position is less, so key is in the second half, so we are updating the value of first. Last will not change, only first will change, so first is equal to m plus 1. If am is greater than key, other case, in that case we'll find the element in the first half. In that case last will update, it will become from last index to m minus 1, the current computed value of m minus 1. Okay, and then we can get a case when at the middle position we are getting this given value. In that case we'll return that value of m, because actually we are interested in finding the index of the element where it is present in the given array. So either of these three conditions will be completed. If we are not able to find out, even this loop is completed, even after this loop is completed, that means the given element is not available in the array. So we'll return a symbolic representation here, return minus 1, that would indicate to the caller of this function that it could not find the key in the given array of n elements. So I hope this code is mapping with the concept, and it is called recursive solution because we are it is called iterative solution because we are making use of loops. We are not making use of any recursive call. So let us move to recursive solution. Recursive solution means we need to call this function from its body either directly or indirectly, but in this case direct recursion we are implementing. Array name is being passed to the function, first index, last index, and the element that we want to search is being passed. 4 parameters in this function. Again last should be greater than equal to first, obvious condition that should be checked before calculating the other procedure. After it is satisfied, we calculate the mid position initially for the given value of first and last. It will calculate integer division, mid, and again the same process we are following. We'll checking whether at the mid position we just calculated is equal to the given key. Then our objective is solved, return the value of mid, that's it. But if it is not the case, in that case a of mid either greater than key, means the mid element is greater, so we have to search in the first half. So here comes the role of recursive call. So we'll again try to check whether for this array which start from the first index up to mid minus 1, because we need to search in the first half. So first will not change and last will come backward up to mid minus 1, and in that array with reduced length of array we'll search the value of key. Now this is the half. Now if the key is greater than a of mid, in that case we'll go to the second half, and for that we'll again call this function recursively for the same array, but now it's truncated from the starting elements because the first index is now mid plus 1. It's not 0, it's mid plus 1, and then it will go up to the last and then key. It's not like that by this call only it will complete. It again depends on how many elements are there in the array and how many times we need to find out the value of mid so that we can reach to this base case. Okay, base case of recursion. These are the recursive calls and this is the base case that needs to be reached in order to stop this recursion, in order to get the result. Okay, so that way through recursion we can implement binary search. Now let us take another problem on which we'll apply iterative and recursive implementation. The problem is famous problem that you must have already seen, is Fibonacci series. It is a special series of numbers which if starts from two values 0 and 1, the third value is calculated from the previous two values by addition of those numbers. So every third member starting from 0 and 1 or every next member is sum of the previous two members of the list. For example, if we start from, as we are calculating from previous two terms, so I am using this terminology last number and second last number from the current number. So if last is 0 and second last is 1, in that case the next would be last plus second last, that is 0 plus 1. So using this formula we can see this series, first two numbers initialized to be 0 and 1, the third value would be sum of previous two 1, 2 is sum of previous two 1 1, 3 is sum of previous two 2 plus 1, 5 is sum of previous two 3 plus 2, and so on. So this kind of series we need to generate either through iteration or through recursion. How we can implement? Okay, we'll see. This is the iterative implementation, or you can say using concept of loops. What I am doing here is I am using two variables to represent the previous two terms, first and second, which is initialized to 0 and 1, and this variable next will be used for calculating the next term. For looping, I am using this variable c. So let us read the value up to how many terms you want the Fibonacci series. Let us read it into n. We'll start the loop from 0 to less than n, because by 0 means the 0th term, that means the 0, and by 1 means the first term, that is 1. These are two terms which are fixed. Okay, so first, second even will use in the else block, but you know that first two terms are predefined. So if c value, which is either 0 or 1, in that case there is no need of calculating the term, we can directly print that. So in that case the next is c, if c is less than or equal to 1. Else next is first plus second. Otherwise, because from third term onwards we need to calculate from the first and second value, last first and second value, whatever it was. So we'll take the last first value and last second value to find out the value of next. We'll keep on, so in this way we'll keep on calculating the value of first and second. Okay, and finally after completion of this loop, all the terms of Fibonacci series would be printed. That was an iterative solution. Okay, so let us move to recursive solution. So in this case, if we want to solve the Fibonacci series, we can make use of recursion, because we need to find out the next term from previous two terms. So in order to find the previous two terms, we can call the function recursively. Okay, let us see how. Again we are reading the value of n for how many terms you want to print the Fibonacci series, and for every this value of I from 0 to less than n, we will call the function Fibo, which we have defined to generate the corresponding term. Here n indicates, or here I indicates the term number starting from 0, 0th term, first term, second term. So this I is being passed as to which term we are referring. So for every value of I, this function is being called. If we have passed the value of I as either 0 or 1, there is no need of any computation, and that will serve as a base case of this recursion. In that case, if n is 0 or n is 1, it will return simply the value of n, either it is 0 or 1, because first two terms are fixed. Otherwise, what we'll do, we will call this function recursively. We'll use this function recursively to calculate the with these function calls with f value 5 and f value 4 again need some computation. So they are further recursively called. F5 would be replaced by F4 plus F3, and again this F4 would be replaced by F3 F2, F3 by F2 F1, and F2 by F1 F0. So every time until the base case is not reached, it will keep on calling further so that it can reach to the base case. So this particular branch, when reaches to F1 is equal to 1 or F0 equal to 0, it does not call further because it is the base case. It is finally calculated, but again we need to find the sum. Plus operation is still pending. For these two calls it will calculate 0 plus 1, that 1 would be given to this 2, and F2 will be completed. This F2 and F1 once completed will give its result for addition to this function called F3, and that will backtrack. So it follows the recursion stack where we follow last in first out strategy. The function which is called at the last is being completed first. Okay, so that way finally it will return back to find out the result for F6. So a number of function calls are being executed when we calculate a particular term. As we increase the term, the number of calls will also increase. That's why we call recursive implementation takes more space, more temporary space in the form of a stack space. Okay. So that was iterative and recursive implementation of some problems. You can implement the similar problems using the same concept for better practice. I hope you will enjoy. So in this session we have seen the concept of